So good morning. Today I'm going to present building and executing ML models at ultra-fast speeds for the particle collider. Um, I'm Claudionor Coelho, and I'm VP Fellow of AI and Head of AI Labs at Palo Alto Networks. First of all, I would like to acknowledge the several people who have worked on this project, namely the group at Google, where I used to work, and the group at CERN, with whom this project was developed. So the agenda of this talk is going to be as follows. First, I'm going to talk about application-specific machine learning, talk about QKeras, a library we created for deep learning quantization, and then how we can use automatic ML or AutoML to search for the best quantization strategy, and introduce some of the key aspects of the AutoML we created, namely forgiving factors, show you some experimental results, and show you how this was used for the CERN particle accelerator, and some conclusions. So when we talk about, when we talk about machine learning acceleration, usually if you have a network like this network here on the left, and you have this a very simple implementation of a dense layer, which is basically a matrix multiplication operation. When you're talking about acceleration, we're talking about a few items. We're talking about what is the memory subsystem you're going to use to store the models, how many bits you need to store, how you're going to execute, and the number of bits and operations that you're going to execute. And in this case, we're talking about max, which is multiply and add. And finally, we're talking about the number of quantization bits that you can use to implement the multiplication and addition operations. So with that in mind, I would like to introduce you the concept of application-specific machine learning. And in the past, people have been talking about generic machine learning algorithms, which they are great. For example, NVIDIA is doing a very good job in pushing for machine learning, generic machine learning acceleration. Google has its TPU that also performs this task. But when you're talking about an application that needs to run at very extreme conditions, maybe it's not a good idea to have a generic accelerator, but to have a very specific accelerator. For example, do you want to specialize the memory subsystem? If you're not required to have a generic accelerator anymore, we can eliminate in the chip the unnecessary routing resources. We can use different quantizations for each processing element, and we can tailor the number of PEs to match the performance requirements. And we are talking about how to get lower area and power and higher performance. And that comes with our definition of what is application-specific ML. First of all, several applications, they can implement it as a static ML models inside the SoC, inside the chip. For example, DRAM scheduler, low power wake-up procedures, IP level QoS, parameter tuning, intrusion detection in an SoC, and etc. And I would like to point to a paper published by Jeff Dean in 2018, where he actually raised the issue that with the advances in deep learning, we could start using machine learning to perform heuristics in a software scenario. And in that sense, we are borrowing his ideas and saying, well, we can actually replace heuristics inside an SoC and replace very costly and error-prone if-then-else chain or heuristic chain by a data flow procedure that is like regular and can be made automatic. So just to contrast general purpose ML and application-specific ML, general purpose ML can be used in several types of applications, while ASML can be used in one or a limited number of applications. Model architecture supports different types of models, different types of arithmetic models. And in ASML, I'm talking about a model that is aggressively quantized. The performances for generic purpose ML It's usually on the millisecond time, and the latency, are talking about millisecond times, and it's variable because it has to interact with the memory subsystem. In an ASML, I want to have like a very deterministic latency, and we want to use the minimum resources that we can use. So in generic purpose ML, we have to talk about fully programmable machine learning, but in an ASML, we can decide which layers you're going to be programmable or no layers being programmable at all, okay? So it's very interesting when I talk to some people and some users about this, they usually come to me and say, oh, we want to have programmable weights. And then when I ask them the question, how do you train those networks? They come to me and they say, well, we use transfer learning. And then after we explain to them that transfer learning is nothing but fixing weights for some layers, they start agreeing that maybe they don't need programmable weights for some applications. So because we're aggressively quantizing the model and getting the model as small as possible, we have a silicon area and power consumption that is very small, whereas power consumption for generic purpose ML and silicon area is usually considered to be large. So there is a paper by Berkeley that talks about how to quantize models. And they actually started by saying that if you want to have like a most aggressive quantization possible, you actually need to think about quantization from the beginning of the model. So usually you have a machine learning model that you start training without any quantization. And the reason why you start doing that is because if your model does not give you good results, you cannot expect that quantization is going to solve that problem for you. And then you apply some quantization to the model, and that's exactly what QKeras does for you. And then you do model optimization. That is like changing the features, changing the layers, creating skip layers, and etc. Okay, and node pruning. And that's exactly what AutoQKeras will do for you, except that AutoQKeras perform this loop back here to change the quantization in an automatic way for you. And finally, you have a synthesis, and we have been working with CERN on a tool they created that converts QKeras models into machine learning for FPGAs. Okay, but actually the model that we create could be used to generate code, could be used in many other contexts as well. So just to start, even if you're going to train initially the model without quantization, you have to start thinking about quantization when you create the first model. Why? Let's take, for example, a popular activation layer called ReLU. ReLU is completely unbounded, whereas we want to have like a bounded version of ReLU, because when you apply quantization, our quantization will have a bounded version of ReLU. Another example is separable convolution 2D, that where the intermediate layers does not have any quantization between the depth-wise and the point-wise convolutions, and actually we want to have a layer that performs at least quantization on the intermediate layers. And third, you should consider always clipping weights during training, because when you have the final model with 4 bits, 8 bits, it's going to be clipped. It's going to have clipped values anyway. So if you apply those 3 rules to start with, you have a good model that is not going to be that hard to quantize later on. So just remember that QKeras gives you a very large number of quantization procedures, and we can basically have mix and match different types of quantizations. For example, we can do exponent quantization and mantissa quantization, and actually exponent quantization, when used correctly, can provide a good trade-off between precision and dynamic range of the arithmetic values, okay? And we have to consider all those things when we are doing quantization. And with that in mind, let me introduce you to QKeras. QKeras is a library that was done while I was at Google, and actually it's available in public domain in GitHub, and it's user-friendly, modular, and composable, easier to understand, minimally intrusive to Keras, and it's easy to learn. And it's part of TensorFlow. If you remember, since TensorFlow 2.0, Keras is a part of TensorFlow, and as such, QKeras can be used in TensorFlow 2.0. So QKeras basically gives you a very large number of layers, and those are like convolutional layers, and you have to understand that right now we have like a recurrent neural networks quantized as well, like QRNN, QLSTM, and QGRU more recently. But what's interesting in QKeras is that it has a very large library of activations layers and quantizers. And to tell you the truth, in this presentation and in QKeras, activation layers and quantizers, they use it interchangeably. Okay. So we have hard sigmoid, hard tangent, hyperbolic tangent, soft sigmoid, soft hyperbolic tangent, quantized bits, Bernoulli trials 0 to 1 with some probability, stochastic ternary, stochastic binary and binary, and then quantized ReLUs, quantized hyperbolic tangent, quantized power of 2. Power of 2 is basically exponent quantization, then quantized ReLU PO2, to name a few. So how do you use QKeras? For example, if you have this layer here, this network here in Keras, you can see the input is like an image, a black and white image, and then you apply those 3 convolutional layers. You flatten and then you just do a dense layer. When you go to QKeras is about tagging weights, tagging activations, so that when we perform the operations in Keras, in TensorFlow, the operations know what are the dynamic ranges of the values. For example, if I have convolution 2D, now I use a quantized convolution 2D, and then I just tag the kernel and I tag the bias. In this case, I'm using a quantized bits, 4 bits, 0 bits to the left of the decimal point. In this case, and actually the activation that I'm using afterward is a quantized ReLU with 4 bits with 0 bits to the left of the decimal point. So it's basically the ReLU is between 0 and 1, but it's not going to be 1 because it's going to be 1 minus 2 to the power of minus 4 in this case. So same thing for the other layers, and at the end they use like a Q dense here. And just to remind that if you're basically thinking about an active inference engine, we don't have to quantize the softmax operation because softmax operation inference, it's not executed. So when you're talking about quantization, we're talking about inferring how many bits you need for the multiplier, for the addition, and for storing the elements. And we have the input size, the weight type, the bias type, and the output type. And based on that, I can decide what is the operation and the size of the multiplier I need to use, what is the operation, the size of the adder I need to use, and then the storage requirements for all those operations. And one thing that QKeras gives you is a way to estimate the size and to mix and match different types of quantizers so that you could have something implemented in floating point, but if both the weights and inputs are basically mantissa quantized, it's like the quantization, then you can perform the multiplication with m bits and then the addition with m prime bits, where m prime is a function of the size of the multiplier output and the number of operations I have to accumulate. But it's interesting because when I started using exponent quantizer, then I don't need to use multipliers anymore. Okay, so if I have exponent quantizer for the weights and exponent quantizer for the inputs, then my multiplication becomes just an adder because I'm adding 2 exponents. And we can go all the way that if you go to weights that are binary and inputs that are binary, then I just need like an XOR operation, then a pop count, pop increment or decrement as implementation of my accumulation. And you can see here that by mixing and matching the different layers with different types of quantizations, I can get more efficient and multiplier-free implementations. So why do I need to search? Quantization itself, it's a very nonlinear problem. And we have to understand that whenever we start quantizing the network, the accuracy drops. And we have too many options to search. Okay. People have tried using reinforcement learning, random search, Gaussian processes. There is this paper from Berkeley that they use the Hessian to try to look at the curvature of the weight space. If the curvature is very smooth, that means that I can use less bits. If the curvature is very steep, that means I have to use more bits. But Hessian itself, it's hard to compute. And you have to understand that Hessian depends on the training. So depending on whether I have trained a layer before and I train a layer after, the Hessian may change the curvature to adapt to the system. So decisions about quantizations before and after a given layer affects how the layer is going to behave as well. And with that, we start introducing the what we call forgiving factors. So if we ask an ML engineer the following question, how much accuracy do you want to lose for deep quantization? Their answer is going to be none. Excuse me. So that actually means that they have the budget of a Fiat 147, but they want to drive a Lamborghini in terms of power requirements, right? They have this huge GPT-3 model that they want to run in your cell phone, but the power budget that you have like 1/10 or 100th of the power budget required to run that model. And then if you change that question a little bit, then the answers become much better. For example, if I ask this following question, if I reduce the power by 10x, are you willing to accept a drop in accuracy of 1%? And it turns out that once you change the question to this question, ML engineers, they start thinking about trade-offs for you. And with that, they can start saying, oh, if you lower the power requirements by 10x, and if I just drop 1% in accuracy, I accept that. And then we capture that exactly the sentence by this equation here. Okay, so this, and basically this equation has the reference cost in power or number of bits or whatever metric you have, the trial cost. We have the stress level because you can say my reference cost is at this point, but I don't want this reference cost. I want a lower starting point than the reference cost for you to be able to give me the best optimization. And then you have the rate and the delta accommodate to this. And then this loss correction factor, it's applied to the accuracy because when the accuracy drops, when you quantize a model, we compensate that in the search process when you compare two different quantizations. So with this, I'm introducing you to AutoQKeras, which is a routine to do automatic quantization. And the first thing that I want to tell you is this. Sometimes you can shift quantization by number of filters and vice versa. Let me give you an example. Suppose that you have this layer here has 64 channels or 64 filters that you want to use. And suppose that I decided that I'm going to quantize this guy using 2 bits, so or 4 bits. So if I increase the number of layers to 96 filters, sometimes I'm able to reduce the number of bits for quantization from 4 bits to 1 bit. Okay, so in that case, if we wiggle the number of bits up and down, we can basically find better quantization models. But what's interesting is this. Sometimes we have to increase, sometimes we have to decrease. Why decrease? Because sometimes when we start quantizing, several of the filters that they look different, they become the same filter. And in that sense, we can actually quantize more. We can reduce the number of filters. So since we cannot tell you beforehand how many, if you have to increase or decrease the size of the model, then we basically put the filter adjustment, the filter tuning inside the AutoQKeras together with quantization procedure. AutoQKeras itself is implemented on top of Keras Tuner, and Keras Tuner have like a random search, Gaussian processes, and hyperband search, and we can actually enable you to use any one of them. My experience is that Gaussian processes, they are very good because they converge faster, but sometimes if you do random search, you can find a better point at the end. But if you just want to run something quicker to get some good enough results, I would choose Gaussian processes. So, but remember, if you're doing random search, even Gaussian processes, if the number of options that you want to try is too large, it will never converge, okay? Because you have to run for a very long time. So how this is like typically a configuration in AutoQCaras where you specify like what are the kernels you want to try, what are the biases you want to try, what are the activations you want to try, and remember what I said between depth-wise and point-wise convolution, that you want to quantize, you want to put a linear quantization there that you can actually replace by different types of quantizers later on. And actually, this linear basically accommodates for that reason. And this is exactly what I had before that I mentioned about the forgiving factors. And in fact, this case, I want to target energy. And I have the delta P and N basically means the delta to the right of the curve and the delta to the negative, to the left of the stress line. What is the rate? Actually, we use to estimate the energy a paper by Horowitz that uses a 42 nanometer. And you can actually specify if your model, the parameters are in SRAM or in DRAM, both for the reference model and for the trial, and activations if they are kept in SRAM or not, or DRAM. Finally, we have to do read and write on I/O. Every time that we have to read the original model and write the original model, whether you're going to consider that we have to read from DRAM or not, or if you want to consider only the power for the model itself. This min SRAM size is that sometimes when you're going to use like a predefined memory cells, there's a minimum size of memory cells. So you're telling the tool that you're not going to infer the smallest size of the memory cell. So for power consumption, we actually try to estimate that. And for the reference model, what is the reference model that you want to use? For example, what is the source quantizers, reference internal quantizers, and what is the reference accumulator? So in this case, what I'm saying is this. The inputs and outputs are int8, and the internal activations, they're int8 as well. Okay, and the accumulator to compute the output, to compute the MAC is an int32 operation. Finally, in this case here, I'm basically saying the dense layer, I'm going to use all the quantizations for kernel using 8 bits, all the quantization for bias using 8 bits, at most 8 bits, I'm sorry, for the kernel is at most 8 bits, at most 8 bits, and for the activations, if there is an activation specified in the layer, at the most 4 bits here. The same thing for convolution, depth-wise convolution, and for activation, I'm just saying if there is an activation layer, just using like 4 bits, and for batch normalization, don't do anything. Actually, we perform batch normalization in a very different way because we always do, we always compute the standard deviation using exponent quantization, because then, and the gamma using exponent quantization, because and the beta and the mean using exponent quantization, because then those operations can be made more compact and you don't have to perform multiplication and division. So without grouping, just doing that with one quantization per layer, that may lead to a very large number of options. So we actually added another option saying, if the layer has this name pattern here, use this kind of quantization. You can see now that I'm basically using just a subset of the items I had before. But if the name is any of the convolutions 1, 2, 3, and 4, group them using the same quantization. What I'm doing is this: instead of having one quantization for each layer, I'm saying just group this using the same quantization. And you do that because you don't want this to blow up the number of searches that you have to do. And by doing that, you can limit the number of searches. So it means that your algorithm is going to converge faster. Because remember, if you have a random search and you have each variable, you have 2 options. And if you have 100 variables that you have to do a random search, I'm talking about 2 to the 100 options to try it out. So it blows up very badly. So we use this group by layer name just to contain it a little bit. And usually I use this when I want to get some initial results to see how much quantization I can get and how much reduction in performance. Reduction in performance and reduction in area I can get with a model. So there is a third method to do scheduling of the operations. And that is called the scheduling groups in sequential order. Basically, what you do, you specify a block here, and your block is any layer name that has a specific pattern applied to it. So in this case, I'm basically, the way I named my layers is like layers ending with 0, layers ending with 1, layers ending with the name 2, 3, and 4. And finally, there is the dense layer. And actually, what I'm basically saying is this. When I order this layer, I compute what is the energy drop that I can get, the energy consumption for each of those blocks. And if the scheduling algorithm is based on cost, it basically picks up the one that has the highest cost first. Why is that? The idea is this, because this guy is going to give me the best result for the quantization if I start with those guys first, okay? Sometimes, if, for example, if you have residual networks, you cannot do that because you need dependencies if you're going to do filter adjustments. So in that case, you may want to do sequential, in which case you basically, we are going to be doing scheduling of the quantizations in this order here. So first blocks that end names with 0, then names with 1, names that ends with 2, and so forth. Okay. So with this, it's like a good trade-off because we do like exhaustive as possible. In this case, like 40 trials for each one of the blocks. But then we reduce, with this, we can reduce the number of options we are going to be randomizing, either for Gaussian process or on the random search. And with that, we can achieve like a faster convergence of the algorithm. And this gives like very good results. So just to give you like some results, this is like a model that we had in a lab that we had at ICCAD recently. And the model is like for MNIST. So you can always argue that it's easy because it's MNIST, but we have applied this to different problems. And you can see that this is the original model size. So you can see here that originally this guy, first convolution has 8 filters, the next one 16, the next one 24, and the next one 32. Okay, and then you get here 128, and then you have like a dense layer for the end. So if you look at the model that we applied quantization, we got, first of all, this model here using the reference model, which is like int8 and int32 for the accumulation, had a power of estimation of 46,823 nanojoules. And after we quantize the model, we obtain the power estimation of 2624. A word of caution here is because our method for estimation of power or energy is completely architecture agnostic. So we basically consider the estimation of the operations execution. We consider the estimation of bringing the first data from the SRAM to the PE to the execution, but we don't consider, for example, that sometimes you use some internal caching because that would depend on the architecture. So if you remember your cache design in computer architecture, this is called compulsory memory access. The first access you have to a given memory address. And we do not consider, for example, surrounding logic that you need registers that you need to estimate the power. Okay, so this model is good as long as you compare two different models, but it's not good to give you like an actual estimation on what is the energy our model is going to consume, because there are several other factors. For example, if you're going to run this model later on an ARM processor, for example, that means that you need to put instruction fat, execution, memory. You have like the whole pipeline that needs to be on while you're executing this model. And for example, this model does not consider that overhead in the energy estimation. However, this model is still good to compare two different models to see what is the energy gains you can get. So basically, let's take the first convolution here. So this one here has like 6 filters. And remember, initially we had 8 filters. Then the next one is 16. And actually the next one was 16. But then we reduced to 12. And this was 24. And the final one reduced it to 16 from 32. So those two here are reduced by half. This one was kept at 16, and this one is 6. Okay. So more interesting is if you start looking at the weights. So the weights here are stochastic ternary. And because I'm using stochastic ternary, even if the input is 8 bits, I don't need to do a multiplication here. Okay. Then the activation for this layer is ternary. and the next one is binary. So that means that it's not even a mux. It's kind of an XOR tree that I have to execute to perform the multiplication here, and the addition becomes a pop count. So the next one, the activation needed more bits, so it's now 4 bits. But I use a stochastic binary for weights, so I don't need to use multiplication. The next one, we have like 4 bits for activation, ternary weights, so no multiplier. And finally, reloop PO2 with 2 bits. So it's like exponent quantization with 2 bits. So you can see here that you don't need to use multiplication. So this network, you can see that we can implement it without any multiplication whatsoever, and you can still get a very, very good result with a memory reduction of 94% of the power. Right now, we only have estimators for power, but you can think that since my power estimation depends on the number of operations and the strength of the operation, you can consider this to be a weak estimator for the area as well. So let's look how we use this at CERN. So at CERN, they have the collider, and in the collider, they have FPGAs at several points, and those FPGAs, they keep logging in data to analyze later on. And they have to make a decision, for example, on if the data passed here, do I have to store this data or not? But they have less than 1 microsecond to make that decision, okay? So initially they have the baseline model. They had like 14 bits with 6 bits to the left of the decimal points used, and they implemented this model. And they used like a Keras model using this kind of quantization, different hybrid quantization. And both of them used DSP resources in the FPGA. And then when they started using QKeras and auto QKeras, they actually implemented, we found like 2 models here. And you can see here that this model still needs a dense operator with 4 bits in the beginning, but this becomes like a ternary. This becomes 2 bits. This becomes stochastic binary. And for those operations here, we don't need to do multiplications anymore, okay? And because of that, the number of bits reduces considerably and the area drops considerably with respect to the original model. This is another idea. Initially, they got an initial model with 14 bits. They tried to do post-quantization training, and the model collapses very easily. And with post-quantization training, what you're doing is that you select a layer and you say, drop the number of bits of this layer from 14 to just prune the bits of the layer and round the values using some rule. Could be using the rule that maintains the norm constant or something like that, but it's basically dropping some of the bits. And you can see here that the model, the accuracy of the model actually dropped very rapidly with the number of bits. However, when using auto QKeras, the model actually maintained the accuracy until much lower than when the accuracy started dropping. Okay, and in this case, we got a model that had 60 nanoseconds latency, 98% reduction of the hardware resources, and 3% loss in accuracy. So it's like almost 50x in reduction by losing only 3% in accuracy. So as conclusions, we're able to show a complete automatic quantization and optimization flow that uses AutoML and using energy as a target, but this energy is also a weak correlation with area. We gave a little bit flexibility to AutoML to do trade-offs between accuracy and lower energy during model search. And then we got some very interesting quantizations that were possible that we did not see before. And auto QKeras trades off model size by quantization in order to obtain the smallest model. And as I mentioned before, the latest version of QKeras includes RNN networks, but we have not seen any people doing yet quantizations using RNNs. Okay, thank you very much for the presentations. And if you have any questions, I'm here to answer them. Thank you.